Hello everyone, welcome to the P1 program. This lecture is called P108.4, right? So in this lecture, what I am going to do basically is that first of all, I'm going to explain what tension is, right? So what tension is, and the second thing is we are going to evaluate tension inside a string, right? A piece of string, what would be the tension at different points of the string? Okay, that's one thing that we are going to do. And the other thing is that I'm going to show you what the tension will be in the case of a suspended string, right? A string with a suspended mass on it, right? And then the last thing is that we are going to use integral and integration techniques to evaluate tension inside a string. Okay, so these are the three things that I'm going to achieve with this lecture. So let's start. So what is tension? So if you have a say rope, right? If you have a rope, then you are pulling on this rope in this direction, right? This is a piece of rope, this has some mass, right? So if you are pulling on this direction with a force, then that force is will be induced onto this piece of rope, right? So there will be a reaction force. If this is an action force, then there will be a reaction force on the right side in the opposite direction, right? So this force will be totally dependent upon the applied force, and this tension is something that if you break this piece up, right? If you break this piece up, then you have again a new reaction force. You say this is the right part and this is the left part, right? So there is a reaction force towards the right, which is F of right reaction. Okay, F of reaction onto the right, on the right side, and then there is an again this reaction force become the action force of the left, right? So action force of the left, so this will be in this direction, this will be in this direction, right? So that's how it breaks up, right? These reaction forces inside and action forces inside will be called tension, right? The forces inside a string or a rope is called the tension. Okay, so that's how you technically define a tension, right? That the force acting inside a rope, right? Now what I'm going to do is that let's assume that we have a mass, right? So we have a mass, say some m1, right? Some m1 mass, and it is attached to a string, right? A string, say it has some mass m2, right? So the gravitational force will be m1g, and the gravitational force here will be m2g, right? And then you are pulling on to this string, right? String from this direction, there is an action force. So if there is an action force like that, then you can clearly acknowledge that there will be a reaction force in the other side of the rope, which you can call Fr, right? You can call like that, right? So F action will be if the string is massless, right? If the string is massless, then F action must be equal to F reaction in magnitude, so it will be in the opposite direction. So F action is equal to minus F reaction, right? So that's very obvious, right? Third law of Newton. Now what I'm going to do is that I'm going to again break up this these masses, right? So what I'm going to do is that let's assume that there is mass, right? The m2 is valid here, right? So if m2 is valid, that means what it means is that if there is an actual mass of the string, then the m1 mass, which is the actual mass which is attached to a string, then this string has some mass. That means it will be induced by the gravity, and it will move, it have to be have some component m2g downwards, right? So that means this will actually make with the direction of force, this is the direction of action force I am pulling, right? So with the direction of force, you can clearly see that there will be an angle of this rope which is subtended. So that angle will be theta, because it is being pulled down, this string or the rope is being pulled down by gravity. That's why there will be an angle, right? That's a physical case, right? Now what we can do is that we can break up this string, right? So what I'm going to do is that I'm going to use, okay, I'm going to break up this string into two parts again. one has, this time I'm going to be fairly technical, one is the left half and the other is the right half, right? So the total length here is L, okay, for the whole thing, right? For the whole thing total length is L and the total mass is m2. Okay, so the left half will, let's assume this length is x, then the other length of the right half will be L minus x, right? So the total length is L. Okay, so that's very easy. So let's call this D. Okay, length D and this is D minus x, right? Okay, so let it be like that. Okay, so in the left part, if you take the left part, only the left part, what you can see is that the you can write down the force. Okay, so now we are taking the left part only, right? So the left part only, when we are taking that, we can write down the equation of force here. So there is reaction force, here is the action force in this direction, and there is the reaction force in this direction, right? So in this part there will be tension here, right? Here will be tension inside the string, which is an action or a reaction inside the string. So you can write down the equation of Newton's second law based upon Newton's second law, and I'm going to take the directions here, right, for notation. So I'm going to take this side as positive and this side, whatever that goes to the left, as negative, right? So I'm taking it like that. Now what I can do is that now I can write down the equation for the left part, right? So Fr is in minus direction, negative direction, so I'm writing Fr, reaction force, plus T of x, right? The tension must be equal to some m of the left part times a of the left part, right? It's very simple. Now now what I'm going to do is that I'm going to find out what ml is, right? M of the left part. So for that I'm going to take a different space here. Okay, so if you have, say, like 10 kilogram, and you split them into half, right? This had the height of 2 meters or 2 centimeters, right? 2 centimeter height. Now if you split up the 10 kilogram, you can easily understand that the weight of this one side will be, what will be the mass of the one side? So it will be 10 kilogram by the total distance, total length, that is 2 centimeters, times what? Times the, I have divided it into 1 times what? 1 times the, what, the distance, this distance, right? This distance is 1 centimeter, right? So this is also 1 centimeter. So what is the mass of this part, 1 centimeter part? So it's 10 by 2 times 1 centimeter, so it will be 5 kilograms, right? So that's an easy way of understanding the same thing, right? So if you look at this plot here, doing the similar thing, you can find out that ml of the left part must be equal to total mass, the same I have done. So total mass is m2 divided by the total length, which is d, times the length here. So the length here is x, so ml must be equal to m2 by d times x, right? So I can substitute the ml value here and I get minus of f of r must be equal to plus t of x, must be equal to m2 by d times x times al, right? So that's the equation here. Let's call this equation 1. Okay, so let's call this equation 1 in another color, equation 1. Okay, now taking the right part, right? If you look at the right part, you can see that in the right there is force, which is action force, which is in the right direction. So I'll say F A in the positive direction, minus Tx, because Tx is in the left side now. Okay, the action forces or reaction forces, the tension due to F reaction was in this direction, right? Because it must be opposite to these the action force or reaction force, so tension will be in the other direction, right? if you don't understand that, then I can simplify it to you. If you pull down from this side, then the force will be acting inside this body on to the other side, right? The inertia will be in the other side. So if this was the action force or reaction force, the tension will be in the opposite direction. If it was the action force, the tension will also be in the opposite direction, the same. So for this case here, right, for this case here, the tension for reaction force was in the right direction, and for tension for the action force was in the left direction, so it will be negative, right? So now you can write down, so for the right part you can see that, so fa, which is the action which is to the right, minus the tension which is to the left, right, T of x must be equal to mr ar, right? So you can write it down like that. So you can now, what you can do is, let's find out the mass of the r. Okay, so fa must be equal to, so mr must be equal to, what is the mass of the right side? So it will be the total mass divided by the total length, which is m2 by d times d minus x, right? So the same as what we have did before. So it will be m2 by d times d minus x, right? D minus x, that will be the mass. So now you can substitute that back into this equation, and you get fa minus t of x must be equal to m2 by d times d minus x times ar, right? Ar. Okay, so we got that equation. Let's call this equation 2. Okay, equation 2. So we have got equation 1 and 2, which is explain the force inside the two things, right? Now what I'm going to introduce now is that we need to find out the tension. That's our objective. So tension is the objective here. We need to find out what the tension is. So I'm going to get back with the mass, right? So these ropes are being pulled down by the mass, right? So if you look at the mass here, okay, if you look at the mass here, it was m1. Let me use a different color. Okay, m1, and there was friction in here, right? So there is friction in downwards. So the frictional force, as you can remember, friction Fr must be equal to some mu of kinetic or static friction. If it's moving, it's kinetic friction times normal force, which is m1g, right? It will be the normal force, which is m1g. Okay, so normal force is to the up in the upwards direction. That's why it's a positive value here. So that will be the frictional force. And so you can write down the equation of Newton's second law for this body itself, right? The mass being pulled by the rope, right? The rope is here and the mass is here. So what the force here is F reaction force, right? So the F reaction force is pulling the mass into a position. Now you can write down the equation for that. So F reaction force is in the negative direction, so minus Fr must plus the mu k m1g, right? Mu k m1g is right there, which is the frictional force to the left side as well. Okay, let's write down symbol in symbol form. So frictional force is to the right. Now it's pulling to the right, right? It's pulling to the right, this mass. So minus mu k m1g, which is to the right, to the left, which is must be equal to some m1 of a1, right? So that's a symbol equation for the mass as well, right? We got three equations and we need to find out the tension, right? So let's call this equation 3. Okay, I hope this part was clear. Now what I'm going to do is that I'm going to substitute equation 1 in equation 3 for Fr, right? Fr value from equation 1. So equation 1 was that Fr minus Fr plus Tx is equal to m2d m2 by dx al, right? So I'm going to substitute the Fr value in here, right? So when you do that, right, when you substitute the Fr in here, what you get is that Fr must be equal to Tx plus or minus m2 by d xal, which is Fr, minus mu k m1 g must be equal to m1 a1, right? So a1, okay, so that will be that. Now I have substituted that. Now what I'm going to do is that I'm going to rearrange this thing, right? So that I get tx must be equal to m2 by d, right? xal plus this goes to the other side, so it's mu k m1g plus m1a, right? So it was simple. Now what I'm going to do is that let's use a different color. So m1a, I got that. Now let's simplify this equation, right? Let's simplify this equation, and I get tx must be equal to some mu k, right, m1g, right, plus m1, I'm taking m1 as common, m1 plus I'm taking a outside, okay, so I'm taking a outside. So let's take, I'm taking a outside because you see, okay, why did I take a outside? Okay, if you see, this mass is attached to this string, right? So whatever the acceleration it has, right, this thing has, if a of the mass or a of the left part, a of the right part, whatever it is, it will all be the same because they are all attached together. So a, l and a r and a will always be the same. So I'm going to take a outside, and I get ml times what, ml times ml plus m1 plus, sorry, m1 plus m2, right, x by d, right, d a, right? Okay, so that's I'm going to call as equation 4, and this is the equation of tension inside a rope, right? So if you look closely at this equation, you can see that the tension is increasing. Tension is increasing with the x, right? What was x? So if you remember, this was the left part and this was the right part, and the x means the distance from the left side, right? So if you increase the tension, if you increase the length x value, then you can clearly see that the tension at this point will also increase. So towards the right, at this point there will be the maximum tension, right? T of x will be the maximum, right? At the left side, the t of x will be the minimum, right? At this point x equal to 0, it will be the minimum. It only has the tension of this part, right? Mu k frictional tension, only the force, frictional force is acting there, nothing else, only the frictional force of this massive body hanging there, right? So that's the only. So tension is actually a varying function inside a body, okay? Tension is actually varying inside a body, and it is going to change with distance, okay? So that's the one thing I need you guys to remember, right? Okay, so now if you look at collectively what the equation of this body was, right? If you want a brief understanding, then you can say fa, which is to the right, right, which is fa to the right, which was the suspend action force, minus the frictional force to the left, right? Frictional force to the left, I'll write it as m1g, right? Frictional force must be equal to ma, where m is m1 plus m2 times a, right? So this was the standard force equation for this body collectively, if you want that. So let's call this equation 5, and you can use that. So we have found out the tension inside a rope. So we did that. Now what I'm going to do is that I'm going to find out the tension in a suspended rope, right? So suspended rope means there is something different. There is an actual case here. So this is a suspended rope, okay? This is a suspended rope, and I'm going to let's call this rope has length L, and it has, okay, let's make it a bit attractive. Okay, this has length L, right? So and let's call this some point y. Okay, let's call some point y, and this is y equal to 0. Okay, y equal to 0, and this is y max, which is L, right? Y equal to L, right? so y equal to L here. So this is a suspended rope, and I want to find out what the tension inside this suspended rope is, right? So what I'm going to do now is very simple, what we have done before. So we know that tension at this point T at y is equal to 0 must be equal to what, mg, right? So it will be equal to mg. That will be the, that's straightforward from the last problem that we did, right? So we can say that this, let's call this equation 6, okay, for reference. Now at an arbitrary point y, right, at an arbitrary point y, we can write down the equation of force, right, equation of motion here. So you can call the, whatever the force here is, that m1g, which is m1a, which is under the influence of gravity here. So T at y equal to 0 minus T of y will be the mass m1, I'm calling it m1 times g, right? This m1 is the mass hanging beneath this surface, right? So whatever the mass inside this point will be determining the tension inside this part, right? So the T of y at 0, so you can clearly say that T of y must be equal to T of y at 0 minus mg, m1g, right? So that will be tension right there, right? So let's call that, okay, let's keep that equation right there, and I need to find out what m1 is, right? So m1 will be, so m1 will be, as we did earlier, m1 will be the total mass, which is let's call it m by the distance, which is L, times the fraction of that length, which is what, y, right? So m1 will be m by L times y, okay. So now you can substitute that m1 back into this equation, and you get T of y must be equal to what, the T of y at 0. What is T of y at 0? T of y at 0 is mg, right? So we can substitute that back as well. So you get mg minus m by L y g, right, which is m1. Okay, we got T here. Now we can take the derivative if you want. This is called the equation of tension for the what, for the suspended string. Okay, so we found that out as well. Now what is the time rate of change of tension? How does tension change? Time rate, not time rate, but the, how does the tension change over this length? Okay, when you come down, what, how will the tension change? Okay, so for that, you, all you have to do is just take the derivative. You get T of dt by dy, so you get must be equal to what, minus m by L g, right? So that's tension, time rate of change of tension. Okay, so this is as well. So we have found out tension inside a string, and also a suspended string, right? A massive string. Okay, now there is an easier way to do all this, right? There is an easier to do all this. So you don't have to do this complicated calculation, but there is a finer and easier tool, which is integration, right? I'm going to represent this is much more harder than using integration. So if you have a string like this, right, massive string, and you can take a fraction of mass, you call it delta m, of fraction of length delta y, right? So for that length, so delta m will be, as we did earlier, delta m mass of that thing will be the total mass by the total length times delta y. Okay, so that's already taken care of. We have did this several times right now. So now the tension at y, so what will be the tension at some point y plus delta y? Okay, what will be the tension at y plus delta y? What will be that? So at some point which is small, slightly more than y, okay, delta y. So at this point, in fact, okay, so at this point it will be T at y plus the change in time, tension, right? So it will be T at y plus the change in tension, so it will be added. So now what you can do is that we can write down the equation, right? So we can write down the equation. Let's look at the equation of force here. So if the string is suspended and it is not moving, right, if it is not moving, then you can clearly imagine that the force will be, so let's call this some force delta F must be plus plus the tension at 2 points. So it will be T at y minus T at y plus delta y. The difference, the tension in between the 2 points must be equal to ma. So if it is suspending and if it is not falling down, then a is equal to 0, then this will be equal to 0. It's straightforward. So delta F will be some delta m times g, right? So it will be some delta m times g, so it will be equal to t plus ty minus uh, minus t of y plus delta t. So t of y plus delta t, as we can say, is this, right? So t of y plus delta t can be written as t of y minus of t of y plus some delta t, that must be equal to 0. Okay, so now you can write down that delta t, right, delta t must be equal to t of y cancels, and you get delta t must be equal to minus some delta mg, right? So now you can write down that delta t must be equal to minus m by L, which is the mass. The mass will be m by L, delta m will be m by L times delta y, right? So minus m by L times delta y times g. Okay, so now what you can do is that you can write it in a different way. Delta t by delta y must be equal to minus m by L g. Okay, so at smaller values of delta y, for smaller changes in y, limit say delta y tends to 0, this will become dt by dy, so that is equal to minus m by L g. So we got that directly. This is the same as equation that we have found out. Okay, we have found out the hard way, so it is the same as equation 8, right? So dt by dy is equal to minus m by L g. Okay, so it's the same thing. So maybe you can do what you can do. If you want to find out the tension from here, you can integrate. You can say dt integral t at y equal to 0, uh, y equal to 0 to t at y times dt of dt must be equal to minus m by L times g, m by L g times integral of this dy gets into the other side, you get y is equal to 0 to y dy, right? So that will be equal to ty minus t at y equal to 0 must be equal to minus m by L g y, right? So it's straightforward, right? Okay, so what you can now do is that we can find out ty. So ty must be equal to mg, which is t at y equal to 0 is what? T at y equal to 0 is what? T at y equal to 0 is mg, right? T at y equal to 0 is mg. So you can write down t of y must be equal to mg minus, this goes to the other side, minus m by L gy, right? So you can write down ty must be equal to mg times 1 minus what, g by L, right? Sorry, y by L. So that will be as same as equation 7, right? So if you look back at equation 7, it will be the same. This is the same. So now we have used integration to find out this thing easily, right? Same as equation 7. Okay, so we have used integration to find out this much more easily now. Okay, so with that I'm going to close this lecture. This was much more mathematical and quantitative. So basically we have learned that tension is actually a varying function, and it is supposed to change with time, change with position inside the string. And next time we will look at the fluid mechanics and the viscosity and all that. Okay,